PBR Automotive, suppliers of braking systems and components to the world market, have produced a series of videos to help understand passenger car braking systems. Following this video on basic braking, the series will continue with diagnostic programs which cover a wide range of customer concerns. These videos will provide explanations of probable causes, together with test and rectification procedures to help in satisfying your customers. A typical modern vehicle will weigh around 1.4 tons, have an engine capacity of 3.5 litres, and be capable of accelerating from rest to 100 kilometres per hour in approximately 10 seconds. To do this, it has sophisticated engine, transmission, and driveline systems. These systems include thousands of mechanical and electronic components, making up nearly half the vehicle's weight. Yet, to meet the expectations of today's driver, the braking system, which usually comprises some 200 components and weighs less than 40 kilograms, needs to be capable of stopping the car from this speed in only 3 to 5 seconds. The braking system is a means of converting the momentum of the vehicle, called kinetic energy, into heat by creating friction in the wheel brakes. This heat is in turn dissipated out to the atmosphere from the brake discs and drums. The ability to absorb and dissipate heat rapidly is the controlling factor in preventing brake fade under severe conditions, such as long downhill braking. Of course, the final connection between the vehicle and the road is the tires, and hence their importance in braking performance. The best braking system in the world will still be ineffective if the vehicle has bald or defective tires fitted. The modern braking system consists of a pedal and booster assembly, to which a master cylinder and proportioning valve are attached. At the wheels, we may find either disc calipers and rotors, drums and brake shoes, or a combination of the two. The system will also incorporate a parking brake, which may be part of or separate from the main braking system, and is usually applied by a hand lever. Consider then how critical these relatively few components are to the safety of the vehicle, and you'll begin to appreciate their importance. As an added safety feature, a number of vehicles are now being fitted with anti-lock braking systems. These are designed to prevent wheel lock-up under adverse road and braking conditions and give the driver far greater control in an emergency. They also add to the weight and complexity of the braking system and will be the subject of a later video. Most larger vehicles today have disc brakes fitted to the front and rear wheels, whilst smaller vehicles may have them fitted only to the front, retaining the earlier designed drum brakes at the rear. Disc brakes are gaining more and more in popularity due to their ability to dissipate heat more rapidly than drum brakes, hence their usage on the front wheels where most of the braking takes place. The wheel brakes are applied by hydraulic pressure. A pressure-producing master cylinder is connected by tubing and flexible hoses to the disc brake calipers or drum brake wheel cylinders. The master cylinder piston can be operated by a push rod connected directly to the brake pedal, or, as is more generally the case, through a power brake booster. This booster increases the application force on the master cylinder piston and reduces driver pedal effort. The hydraulic pressure generated in the master cylinder is transmitted via pipes to the individual disc calipers or wheel cylinders. These, in turn, bring the lining material in contact with the discs or drums to generate the braking force. The amount of force generated on each set of brakes is determined by the area of the hydraulic pistons, the design of the brake, its size, and type. A tandem or dual master cylinder is one of the vehicle's most important safety devices. It operates a divided or split hydraulic system, and is designed in such a manner that if one circuit fails, the other still operates, leaving the driver with a portion of the total braking capacity. Generally, on front-engine rear-wheel drive vehicles, one hydraulic circuit of the tandem master cylinder operates the front brakes, whilst the other operates the rears. This type of vehicle usually has 60% of its weight acting on the front wheels and the remaining 40% acting on the rear wheels. In the case of a brake failure in one circuit, the amount of braking force available would correspond to the amount of weight on the axle. On front-engine, front-wheel drive vehicles, the weight distribution is significantly different, with about 80% of the weight being on the front wheels and only 20% on the rears. To allow for the possibility of a single circuit failure, a diagonal or cross-split layout is used. This has one front wheel and the diagonally opposite rear wheel connected to each circuit. Should either circuit fail, an equal amount of braking will still be available. It would still, of course, be only half the normal braking force of a fully operational braking system. Most tandem master cylinders incorporate a warning switch to warn the driver of a circuit failure. Also, within the cylinder housing is a proportioning valve, or valves which automatically reduce the hydraulic pressure to the rear wheels. This provides balanced braking at all stopping rates and prevents rear wheel lockup. Some vehicles' master cylinders may also incorporate a fast fill valve, sometimes referred to as quick take-up. This provides reduced pedal travel in modern systems, where the clearance between the pad and disc rotor is greater than in the past. The greater clearance gives less drag and hence improves fuel economy. As we have previously mentioned, most locally produced passenger vehicles have proportioning valves integrated within the master cylinder housing. This is done to reduce the weight and complexity of the hydraulic piping. There are exceptions to this, and proportioning valves may be remote from the master cylinder. Proportioning valves come in different types and may be classified as single or dual, pressure sensitive, deceleration, or load sensitive. The need for proportioning valves is due to the weight transfer that occurs during braking. Under braking, the nose of the vehicle dips as weight is transferred to it, and the rear raises up as weight is removed. This necessitates a reduction in hydraulic pressure to the rear wheels. Where a large variation in axle loading at the rear takes place, such as in station wagons, utilities, or goods-carrying vehicles, a load or height-sensitive proportioning valve is generally fitted. When axle load is low, the hydraulic pressure required at the rear wheels to produce the necessary braking force is also low. As the load on the back axle increases, so does the amount of pressure needed to the rear wheels. The load-sensing proportioning valve achieves this requirement. As an added safety feature on vehicles with a front-rear split braking system, proportioning valves may also include a bypass feature. This automatically allows full pressure to the rear brakes in the event of front-wheel brake system failure. Braking is one of the most repetitive functions when driving a motor vehicle. The requirement, therefore, to reduce the effort involved led to the development of the brake booster. A readily available source of vacuum exists in the manifold of all four-stroke petrol engines and is utilized in the brake booster to help reduce the pedal effort. Diesel engines, on the other hand, do not produce a vacuum in the inlet manifold and therefore require some external devices to provide the necessary vacuum. In this case, a vacuum pump driven off the back of the alternator is employed. The brake booster is mounted to the vehicle firewall between the brake pedal and the master cylinder. Brake boosters vary in size and may be either single or double diaphragm type, depending on the amount of assistance required. A brake booster can increase the amount of force applied to the master cylinder by 3 to 5 times, and yet still maintain braking sensitivity and response. Brake boosters contain a front chamber, which remains at constant pressure, and a rear chamber in which the pressure varies. These two chambers are separated by a pressure plate and valve body, and are sealed from each other by a rubber diaphragm. A control valve, operated by the pedal push rod, regulates the amount of atmospheric pressure let into the rear chamber. This control valve, which also includes a vacuum valve, is directly connected to the output push rod. A vacuum non-return, or check valve, is fitted either to the booster or in the hose from the engine manifold. If for any reason the engine should stop, this valve retains enough vacuum in the booster for up to 3 brake applications. In the case of a total loss of the vacuum supply, the control valve rod assembly and output rod act as a single push rod. The brakes will therefore continue to work, but the driver will have to push considerably harder to stop the vehicle. Foot or service brakes are used to stop or control the speed of a vehicle. Parking brakes, on the other hand, are mainly used for holding the vehicle stationary or for helping start off on a hill. The braking, descending a long hill or during repeated stops, must remain as constant as possible. The brakes must therefore be able to absorb enough heat to prevent excessive temperature buildup. A large controlling factor in this is the size of the discs and drums. Also, directing maximum possible volume of air over the brakes will help keep temperatures within the limits of the brake fluid and lining material. As has already been mentioned, the majority of modern vehicles are adopting the 4-wheel disc brake layout. The once popular front disc, rear drum combination is now being relegated to the current range of mid and smaller sized vehicles available on the market. Whilst in the past, parking brakes have traditionally been incorporated in the rear caliper or drum brake assembly, a growing number of vehicles now have a separate brake assembly fitted inside the disc for that purpose. The inherent stability and consequent increase in safety of the disc brake has led to its almost universal usage on passenger vehicles today. A disc brake in its simplest form consists of a cast iron rotor which rotates with the wheel and 2 fixed pads to which friction material is bonded. When the driver applies the brakes, pressure developed in the master cylinder forces these pads against the rotor. The resulting friction between the pads and the rotor develops the braking force necessary to stop or slow the vehicle. The amount of braking force generated is controlled by how hard the pads are clamped against the rotor. Because most of the disc rotor is exposed to the air, heat produced by friction is easily radiated away, minimizing brake fade and ensuring braking stability at all speeds. If the vehicle is driven through water, it recovers to full performance quickly due to the water being thrown off the rotating disc by centrifugal force. The disc brake caliper holds 1 or more pistons which, when pushed by hydraulic pressure, force the pads against the disc rotor. These calipers may be either fixed head opposed piston design or floating head single piston type. Variations of fixed head calipers may have 4 opposed pistons, whilst some floating head calipers may have 2. Multiple pistons are used when larger forces are required for special applications, such as heavier or high-performance vehicles. The disc rotors themselves may be either a solid or ventilated design, again depending on the application. The ventilated design, having more surface area, radiates heat more readily, making it more suitable for heavy-duty applications. Another important feature of the disc brake is that it provides continuous, automatic adjustment for the life of the pad. This eliminates the need for periodic brake adjustments by keeping the clearance between the pad and the rotor constant. This applies to all disc brake calipers, including those incorporating integral parking brakes. In the drum brake, just as in the disc brake, force is generated from hydraulic pressure developed in the master cylinder. This pressure acts on one or more wheel cylinders, which in turn forces the brake shoes against a drum which rotates with the wheel. These brake shoes, which have the friction material attached to them, are anchored to the backing plate and are therefore prevented from rotating. It is the pressure with which the brake shoes are forced against the rotating drum which controls the amount of heat produced and hence the braking force generated. The most common type of drum brake assembly fitted to the rear wheels of today's modern vehicles is the leading and trailing shoe design. This has gained favour over the earlier duo servo design, although both types feature automatic adjusting systems. Both types also provide a parking brake, whereby the brake shoes are expanded by a lever and strut mechanism. The lever is connected by a cable to a park brake lever located near the driver in the passenger compartment. The force applied by the driver is usually multiplied by an intermediate lever, and an equalizer is also incorporated to ensure the same amount of force is applied to each brake. PBR Automotive trust that the basics of braking has helped provide an insight into the braking systems which play such a vital role in today's motor vehicles. For a more detailed description of how the components covered by this video work, or how to diagnose faults, we refer you to the other diagnostic videos in this series.